All right. So when we were proving this statement, right? We said let x be arbitrary, let y be x+1, and then we just stated without proof that x+1 was greater than x. And one might say, how do we do that, right? So we just took it for granted. We just said we're working over the reals, we're working over the integers, and this is something that's true there. But really, really, we, how do you know what's true over the integers, over the reals? How do you know that? And so what we do instead, we have to give axioms, and yeah, there's lots of complications involved, but we'll just think about it a little bit. All right. Right. Try to get a picture of what's going on here. All right. So here. So let me ask you a little quiz here of high school math. All right. So the first question is what's our first question? Not up there yet. All right. Is the sine of 90 1? And you can think about it, and maybe you remember, and the answer is yes. Then you can go to calculus, and you can ask, is the derivative of sine cosine? And you'll probably say yes, right? And then you can ask, this is just a question that combines the two, right? If the first is true and the second is true, then we can combine them in a sum. And what about this one? Is this one true? If you say, is the first and the second both true at the same time? Any idea? All right. Well, they're not true at the same time. All right. The first one assumes that the circle is divided in 360 degrees, right? We're doing it in degrees. And the second one, what is the second one measuring it in? The angles. Remember? Radians, right? The second one assumes we're doing it in radians, right? And so the point is, you can decide maybe what model you're in, but you can't be in both models at the same time, right? One of them has to give. All right, so here's our statement, right? Right, we want to know if x+1 is bigger than x. Well, it's a negation. Everybody will say, well, the negation is false, right? So it must be true, right? What does true mean? Remember what true means? True means in this model that we're considering, it's true. It's a specific model, right? When you plug in all the values, it becomes true, right? But to be valid, it has to be true in every possible model, right? So then we can ask this, is x+1 bigger than x in every possible model? What do you think? Well, it's certainly true, say, over the reals, over the integers, over the complex numbers, it's true, right? But can we think of an interpretation where it's false, right? We just need to come up with one model in which it's false and it's not valid, right? So let's think about what we're saying here. Well, first off, x is a free variable, so we're saying every x. And we're also saying every model, right? And what does the model include? Model includes what is the set of objects that we're talking about. The model defines what plus means, right? We don't even know what plus means, right? Model defines what greater than means. The model defines what 1 means, right? So proving it for all models might be hard, right? Proving it's not true for one model is easy, right? So here we just want to say, we want to prove there exists a model in which it's not true, right? So if our universe has these, integers, then it's true, right? Suppose we just add into our universe infinity, right? It's an object. We call it infinity. What are its properties? Well, one of its properties is that if you add 1 to it, you still get infinity, right? So it's not true. Right? I don't know if you've done integers mod 5, say. Well, in integers mod 5, you can add, right? 4 plus 1 is 0, which is 0. And so 0 is not bigger than 4. And so it's not true under the integers mod 5, right? Here's another model which I made up. Suppose our objects are the devil, God, and you, and we define marriage plus to be marriage, right? And we define greater than saying something is better than something else, right? And 1 is the devil, all right? So then what does this mean? This means, right, x, whatever x is, let you be x. X plus 1, that means you're being married to the devil is better than you by yourself, right? So, right? So then you want to know, is that true or not? Well, it depends on your view of things, right? So here, if we're working over the integers, it's true, right? Well, now we don't need to say it's valid, because if I say we're working over the integers, we have a specific model, and we can say that it's true, right? And and that's true. If we work over the positive integers, right, then the first one's true, but the second one, x minus 1, doesn't even have a definition when x is 0. Yeah? Yeah, we're going to get there. So the way you have to make things valid is by making assumptions, right? We'll have a whole bunch of axioms or a whole bunch of assumptions. And if all these things are true, then all these things are true, right? So you're kind of right. Just one statement by itself is not likely to be valid, right? So that's false, right? If we, in this case, they're both false, right? Everybody kind of buy this? All right. So what are we trying to do here with formal proofs, right? We want to have as few as, we're going to have assumptions, right? We're going to have as few assumptions as possible. And the advantage of doing that is that then there may be a number of cool models which in which your axioms are true, and then the things that you prove will automatically be true, right? Right. So how do you prove anything, right? That's the question. So in a formal proof, right, the first method that we were doing up until now is we were just saying, oh, we're working over the integers. And then we say, well, this is true. We know it's true over the integers, right? And that begs the question, well, what are you allowed to know are true over the integers, right? The method, the more standard method is you have some axioms that you decide are true, right? Right. We want to prove that this sentence is true. And how do we prove it? Well, we can say, well, in the integers, what things are we confident? Suppose we want to prove it's true over the integers, right? We say, well, over the integers, what things are we pretty sure are true? In fact, in some ways, what we have to do is we have to define the integers, right? The word integer is just a bunch of letters. Somebody has to tell you what the integers are, right? So we can make up a large set of axioms, which we say these axioms are true. We believe are true over integers. We're going to claim that the definition sort of integers is that these things are true, right? And then from these axioms, we're going to prove our statement alpha. And that proves to us that in any model in which these axioms are true, alpha is true, right? And since we know, or at least it's our belief, that these axioms are true under the integers, then we know that our sentence is true under the integers, right? Does that make sense? Everybody kind of follow that back there, right? So it's kind of like we have, oh, I was sitting at home and there was chalk on my desk and I put one in my pocket, right? So here's the set kind of all universes, right? And then we define a bunch of axioms. And these are the universes which are true about, these are the set of universes that the axioms are true, right? And we prove that if the axioms are true, then alpha is true. So here's the axioms. So actually, here would be a good question to add to the exam, right? Does this picture imply that if the axioms are true, then alpha is true? Or does it imply that if alpha is true, the axioms are true? Yeah, if we're inside the if we're in a universe in which the axioms are true, right? Then we're in a universe in which alpha is true, right? And the integers is a model, right? So where does the integers lie, right? Here's z is the integers, I don't know. So here's the integer sitting right there. The axioms are true, and his alpha is true, right? But it could well be that the integers mod 5, the axioms are also true, right? And so then alpha is also true for the integers mod 5, right? Does that make sense? In fact, what's common is that these axioms might be the axioms for what we call fields, right? And there are many fields. The complex numbers are a field. The reals are a field, right? And then we prove that alpha is true for any field. Everybody good? All right, so these guys here, right, we kind of proved them. And we're going to add them to our axioms, right? And I added lots of them, lots of axioms. Why did I make such a big table? Do we need them all to be able to prove things? No, you can prove them from a few things. But I wanted to make your life easier proving things, so I made a big table, right? And then we can add non-logical axioms, which might be the axioms for, say, for a field. Right? So here's some, let's see. Right? Oh, this just says, right? What does this say? We say, here are our axioms, and from our axioms, I always forget, one of these symbols is proof, and one of them is true, right? So anyway, what does it say here? We said for any, it's true, right? In any universe, any model in which the axioms are true, for it, then alpha is also true, right? It said if in any model where the axioms are true, right, the the sentence is true, right? And this is about proofs, right? This says that if you start from the axioms, then you can prove things, right? You can have a proof where you build on the axioms, right? And soundness means if you can prove it, then it's true, valid, and the other direction is completeness. If it's true in every model, then you can prove it, right? All right, so here let's think of some axioms, right? We're trying to build the integers, or maybe we're just trying to build the positive integers, right? So what are we going to say? Well, 0 is important. Let's have an axiom that says 0 exists, right? And then we have to have the idea of the next guy, right? So we can say, we define a function that you give it any object I, and our idea is that what it returns is the successor, right? And from those, you can think, what do we get? Well, we have 0 because we made it. And that gives us 1, that gives us 2, right? We get all of these objects, right? Does that make sense? And we can define, oh, all of these things are true for the integers, right? But be careful. Here's a funny thing that Gödel proves, is if you throw in any finite set of axioms that are true for the integers, you think, if I throw in enough of them, I will narrow down to, I'm only talking about the integers, right? And what he proves is that if you only throw in a finite number of axioms, there will always be some non-standard model which you didn't intend to be around. All right? And is that a disaster? No, it's not a disaster. There's always these weird universes out there. But if the axioms are true in that weird universe, right, then your alpha is still true in that weird universe. Right? All right. Now, we also want plus and times, right? So we want to say, what do we know about plus and times? Well, we can talk about, we have an additive 0 and we have a multiplicative 1, right? What properties do we want of those, right? We can say we want things associative, we want things commutative, we want things distributive, right? We want there to be, if there's a B, we want there to be if there's an A, we want there to be a minus A, right? So those are all axioms that we can add. Right, everybody buy that? And now we have to define bigger than, right? Well, this would be a reasonable axiom, right? We could start off saying A plus 1 is bigger than A, which of course then we get this for free because it's one of our axioms, right? And then we can say, well, we need to, again, we're back to induction. Remember, what we're going to be learning next is more about induction. And that's kind of what we're doing here. We're defining greater than by induction, right? The base case is that A plus 1 is bigger than A, right? And then, well, what about A plus 2? Is it bigger than A? Well, we're going to say A is bigger than, if A is bigger than B, then A plus 1 is bigger than B, right? And how does that work? Well, we know already that A plus 1 is bigger than A. Hence, A plus 2 is bigger than A. And A plus 3 is bigger than A. And A plus 4 is bigger than A. Right? Does that make sense? We're kind of proving it by induction. People kind of following that? Yeah. Well, what happened here when I was making the slides, I threw in a really easy example, right? And then when I was writing down the axioms, it also became an axiom, right? So in that case, yeah, it's trivial. But in general, if I wanted to prove something complicated, if I threw it in as an axiom, then I haven't really proved any much, right? So this is just a trivial example, right? And again, it's just one line of our proof, right? We're proving something big and complicated, right? Right? And this is just one line of the proof, right? So here we get it as an axiom, right? And then from that, oh yeah, so here's some more fun examples, right? So we have this as an axiom. What can we prove from it, right? Well, remember you're allowed to, this x is, actually x plus 1 is an arbitrary term, right? And it's not free, we don't have any for all bugging it up. So we can just say, hey, if x plus 1 is bigger than x, then there exists the y that's bigger than x, right? Everybody see how we can just add the exists, right? Right, and then we can say, now we have a free variable x. So we can say for all x, there exists the y, right? And that's what we were looking to prove, right? And so this says, we prove this sentence from the axioms, and hence this sentence is true in every model in which your axioms are true, right? So, for example, the integers is a model in which these axioms are true, and hence this statement is true over the integers, right? I keep repeating myself. Right? Right, so yeah, mathematicians have been adding axioms all along, right? And seeing what they can prove from it. And what they want to do is they want to add enough axioms so that they can prove everything about the integers, right? And so Gödel, he proves two things. He proves his completeness theorem and his incompleteness theorem. All right. So I think these are really worth knowing because they're kind of foundational to mathematics, right? He proves that if a sentence is true in every model, then there's a proof of it, right? But he also proves the incompleteness theorem. He says about the integers, right? If you want to prove things about the integers, there's no finite proof system that can prove everything about the integers, right? Why? Because there's always these weird models in there, right? All right.